The coffee machine. How does the machine work? It's more than hot water. It's pressure, heat, flow control, a small engineering marvel. It starts with water. The reservoir stores it, usually a plastic or glass tank. Cold water sits ready. One valve controls the draw. That water is the base. Next, heating. A metal coil wraps a tube. Electricity runs through the coil. It glows with heat. Water inside the tube warms. Temperature climbs fast, usually near 90 to 96 degrees Celsius. Now, movement. A pump drives water forward. In drip machines, air pressure pushes. In espresso machines, an electric pump. Pressure builds from 1 to 9 bars. That's strong enough for extraction. The water travels upward through narrow tubes into the brew head. Pressure keeps flow steady. Temperature is monitored. A thermostat avoids overheating. Consistency is the goal. Next stop, the grounds. Fresh beans are ground. Particle size controls flow. Too fine. Clogging, bitterness. Too coarse, weak, watery. A filter basket holds the bed. Even distribution is critical. In espresso, a pause. A small splash wets the puck. This is pre-infusion. It lets grounds expand, channels close up, the bed becomes even, extraction improves. Now the main brew. Hot pressurized water flows, compounds dissolve fast, acids, sugars, oils, each contributes flavor. Balance comes from timing. Too short, sour. Too long, bitter. Ideal, 25-30 seconds for espresso. Drip machines differ. Water drips, not pressured. Gravity pulls through grounds, slower extraction, cleaner taste, less body. Espresso uses pressure, dense, rich flavor forms. Temperature precision matters. Too hot, harsh flavors. Too cool, sour taste. Machines use thermostats, high-end models, PID controllers. They lock temperature tightly. That stability shapes flavor. Every brew is engineering. Tiny systems working fast. The next sip you take, you'll know the science inside. Next, a toaster. This is a toaster, a simple appliance. But inside, it's clever engineering. Let's see how it works. Bread slides into the slot. Guides hold it upright. Even spacing is key. The lever pulls the slice down. At the same time, it closes a switch. Now electricity can flow. The lever compresses a spring. The spring stores energy. Later, it will release. That release is what pops the bread up. Pushing the lever closes the circuit. Power flows from the outlet. Current moves into the toaster, directly toward the heating elements. The elements are nichrome wires. Nichrome resists electricity. Resistance turns energy into heat. The wires glow bright orange. They radiate infrared energy. This heat is what toasts the bread. Wires run along each slot wall. Reflective metal surfaces sit behind them. Reflections bounce heat back to the bread. Both sides of the slice heat evenly. Heat leaves the wires as radiation. It strikes the bread surface. Moisture starts evaporating. The crust dries out. Soon, browning begins. Around 140 degrees C, chemistry starts. It's called the Maillard reaction. Sugars and proteins react. Brown color forms. Flavor compounds build. This is what makes toast taste good. How does it stop in time? Older toasters use a bimetallic strip. Two metals expand at different rates. As they heat, the strip bends. At a set bend point, the latch releases. The spring pops the toast up. Modern designs use electronic timers. Sensors monitor heat inside the slot. Some measure resistance of the wires. Others track ambient temperature. Electronics cut power precisely. When the cycle ends, the latch opens. The compressed spring expands quickly. The lever lifts the bread. Toast clears the slot. No extra heat is applied. Toasters include thermal cutoffs. If elements overheat, power is cut. Fuses prevent electrical faults. Casing stays insulated. And crumb trays prevent buildup from igniting. Crumbs fall during toasting. A tray collects them at the bottom. It slides out for cleaning. Removing crumbs keeps airflow smooth and prevents stray burning. Wide slots handle thick bread. Some toasters have bagel mode. More heat on the cut side, less heat on the crust side. That way the inside crisps, outside stays soft. 2-slice and 4-slice toasters differ. Larger toasters use paired circuits. Each pair controls 2 slots. Independent timing keeps the slices even. That's a toaster in action. Simple outside, precise inside. Electricity, resistance, and heat all working together. Every slice, consistent toast. Next, a microwave. Microwave ovens. Almost every kitchen has one. But how do they actually cook food? It's not heat from a bulb. It's not dangerous radiation. It's waves. Invisible waves bouncing inside. Microwaves are electromagnetic waves. Same family as light, radio, Wi-Fi. The oven runs at 2.45 gigahertz. That frequency couples with water molecules. And food is mostly water. So the waves target water directly. Water molecules are polar. One end positive, one negative. Microwaves flip polarity billions of times per second. Molecules twist back and forth. That motion creates friction. Friction becomes heat. Heat spreads through the food. Not all frequencies work. Too low, nothing happens. Too high, energy passes through. 2.45 gigahertz hits the sweet spot. It penetrates a few centimeters, strong enough for molecules, but safe in the kitchen band. Where do waves come from? The magnetron, a vacuum tube with a strong magnet. Electrons swirl in circles. Spinning generates microwaves. Energy travels through a waveguide into the cooking chamber. The chamber is a Faraday cage. Waves stay trapped inside. Food absorbs the energy. The chamber is like mirrors for waves. They reflect and overlap. This creates standing waves, hot spots and cold spots. That's uneven heating. Turntables move food through zones. Mode stirrers scatter waves. Both improve energy spread. Microwaves don't just cook surfaces. They reach 2 to 4 centimeters in. Outer layers absorb first. Inner layers get wave energy too. Then conduction spreads deeper. Food heats inside and out. Edges heat more than centers. More surface exposed to waves. Corners focus wave energy. That's why crusts get hot. Centers can lag behind. Stirring balances heat. Not every container is safe. Metals reflect microwaves. Flat sheets shield food. Sharp edges spark. Plastics, glass, ceramics let waves through. They heat less themselves. Thin plastics can warp. Always use microwave safe. Never seal containers tight. Pressure can make them burst. Waves are trapped inside. Walls are solid metal. The door has fine mesh. Microwaves are 12 centimeter wavelength. Mesh holes are much smaller. Light passes, but waves cannot. Does microwaving kill nutrients? Any heat can reduce vitamins, but microwaving is fast and gentle. Less water, less loss. Often more nutrients remain. And no, food isn't radioactive. Waves vanish the moment power stops. Food can burst inside microwaves. Liquids superheat without bubbling. Disturbance releases steam violently. Dense foods trap pockets. Pressure pops them open. Poke holes to vent. Best for reheating and steaming. Great for veggies, butter, leftovers. Not for crispy textures. Crisp needs dry high heat. That's where pans still win. Microwaves cook with waves. Magnetron generates 2.45 gigahertz. Water molecules absorb it. Molecules vibrate, friction heats. Chamber bounces energy. Turntables even it out. Fast, efficient cooking. Every press of start uses physics. Clever waves at work. Next time leftovers spin, you'll know what's happening inside. That's the science of microwave ovens.